So hello everyone, I'm Angelos Kalias, Chief Scientist at Input Output and Chair in Cybersecurity and Privacy at the University of Edinburgh. I'm joined in this panel by four of my colleagues at Input Output who will now introduce themselves.
Hello, my name is Manuel Chakravarti and my background is in programming languages, compilers and high-performance computing. At IOHK, I've been leading the research into the Bluetooth smart contract system together with Phil Wadler.
Hi, I'm Michael Baton-Jones. I'm the team lead for the Bluetooth team at IOHK, also with a background in programming languages. And so I've been working mostly on Bluetooth, but also I have a keen interest in what's going on with the ledger, hence this talk.
Hello, my name is Nikos Karagiannidis and I have been a research fellow at IOG since 2018. I have a database research background, but lately I have been doing research on blockchains in the area of decentralized software updates in the context of a European research project called Privilege. Among others, I have recently worked on the problem of the maintenance of the state in the distributed ledgers.
Hello, my name is Paulina Vinagradova, and I have been a formal method software developer at IOHK since 2018. I have a background in formal logic, and throughout the time that I've been here, I've been working on formal specifications of the ledgers for different eras, including Shirley, Allegra, Mary, and Alonzo. I was also the TA/co-instructor for the all-female Haskell course run by IOHK in Ethiopia.
All right. So let's get started on our topic. Accessing any blockchain platform requires some expenditure on the user side. Now, this is essential first and foremost from a security point of view. Think about denial of service. If access is completely open, nothing prevents an attacker from saturating the network and blocking access at will for everyone. This is also important, though, from a point of view of platforms' economics. Blockchain operators need to be able to offset their costs by receiving digital tokens that should derive value from somewhere. Now, users acquiring such digital tokens to transact creates a demand for them, and hence they become valuable. A natural way to do this can be seen in Bitcoin. Users put Bitcoin in their transaction and engage in a first price auction. Miners select the most valuable transactions to process, and then they create a block. While this is straightforward, it has a number of shortcomings. First, transaction prices are not stable and they're not predictable. This limits the ability of users to budget their operations. Second, platforms such as Ethereum and Cardano are meant to be used, among other things, to create user-defined applications that have their own tokens. And users of such apps may not have or even be able to acquire the platform's main token. So how can they transact with such a system? Manuel, why is this important and what are the main considerations?
If you look at ecosystems like, for example, Ethereum's, then we see that custom currencies are really one of the main applications of these types of platforms at the moment. And the DeFi infrastructure built on top of all kinds of currencies is another witness of this development. And we've seen since the launch of custom tokens on Cardano with the Mary hard fork that also on Cardano this is a very popular way of using the platform. Now, one reason why people develop their own currencies is because they're developing apps that are powered by these currencies or where holders in custom currencies have governance rights or other ways of influencing or using the platform. So they come with their own ecosystem, if you like. Just as an example, imagine multiplayer games. Very often in multiplayer games, you've got some in-game currency, and then there are various types of items you can gain by managing to get some achievements or also by purchasing them. And then very often we also want players be able to trade these items among themselves. So really we have a sort of custom marketplace with a custom currency. Now, in such a situation, why would we expect for a game where these monetary transactions are done on Cardano for the players to hold ADA? Their main interest is in this game and not foremost in the Cardano blockchain. So they will have the in-game currency, but they won't have ADA. And that's a problem because, as you've just explained, Aglos, the currencies and paying with currencies for transactions is a fundamental principle underlying those blockchain platforms. So we really have to find a way to get people who don't own the primary currency but custom currency to be able to pay for their transactions, even if that comes with the additional problem that there will always be a risk with respect to the exchange rates.
Thanks, Manuel. So the first platform to enable general purpose custom tokens was Ethereum. And general purpose here means that you can basically program the tokens to operate in any way the designer wants. So this raises the question, is it possible to implement paying fees in custom tokens in Ethereum? Paulina?
Ethereum supports fee payment in non-primary currencies via its gas station network. So the infrastructure for the gas station network consists of a network of nodes listening for meta transactions, which are transaction-like requests to cover fees. These nodes turn these requests into complete transactions with fees covered by the relay node, and an interface that contracts must implement in order for the relay nodes to use this contract funds to subsidize the transaction fees, which means construct the full transactions with those funds. So the gas station network requires a few actions to be performed, including disseminating partially formed these meta transactions on a separate network. It requires building infrastructure which is additional to the existing blockchain infrastructure, such as the relays, hubs, and separate communication network. And it also requires changes to smart contracts in order to allow them to participate in covering fees of transactions that engage with them. And it also, and then submitting of the transactions also to get their fees covered also requires the user to pay attention to what's going on with the transaction later. And in addition, this gas station network requires that prepaying, that the fee amounts have to be prepaid into contracts that willing to cover the fees. So yeah, so these are kind of some of the main points of gas station.
Thank you for covering this. So Cardano's user-defined token model, though, is completely different, right? It has a way of defining user tokens at the same level as the native currency of the system. And this enables a completely different mechanism actually to be implemented. So this is something that we've developed as Babel fees. So Babel fees is based on the idea of a spot swap of a user-defined token that is allocated as fees in a transaction. And the swap outputs ADA, something that allows the system to still perform its rewards accounting using its native base currency. So this is completely in line with the proof-of-stake discipline. Now this logic sounds a lot like a DEX. So is this possible to just do it with a conventional DEX, Paulina?
So a conventional DEX does offer similar functionality in many cases, but using a DEX is relatively slow, and the mechanism we're going to detail doesn't require waiting for transactions to be posted on-chain, only that they're disseminated as full transactions across the network, which is faster. So another thing that a DEX requires is a lot of changes to the ledger, which we have to make sure that which in order to implement have to be safe and secure. So implementing a DEX on the ledger rather than a smart contract makes it more difficult to maintain important ledger properties such as determinism or of transaction application. Our approach requires minimal changes to the ledger, so it's easier to show that it does not compromise existing ledger properties or make it susceptible to other adversarial behavior.
Thanks, Paulina. But still, like doing an exchange like the spot swap is at the heart of the idea. So someone will have to engage and want the custom tokens. So who might be that party? Michael?
So there's a few options here. In principle, the mechanism that we designed could work with any number of counterparties in this system. But we noticed that in the system that we have today, there are a number of agents in the system who are actually in a perfect position to act as the other side of these swaps. And those are block producers, because they already have a queue of incoming transactions in the mempool. They potentially have a reasonable amount of capital on hand and might be willing to perform exchanges for particular tokens that they consider to be valuable on a case-by-case basis. And since they're in the process of constructing a block, by making clever choices about which trades to take, which other transactions to include, they can ensure that they maximize their own profits overall.
But now let's come to another aspect which is very important here, and this is price discovery. How do users know how to pay in a certain custom token that is of interest to them? I mean, there are so many and there are so many options. So let's take an example. Let's say we have Alice that would like to transact with the system, and she just happens to hold Bob coins, and she wants to use them to pay for the transactions. Now, block producers, who in our case will be the Cardano stake pool operators, let's say they are willing to process transactions in Bob coins, and they will advertise this publicly, including the exchange rate between Bobcoin and AIDA that are willing to accept. So, Nico, how this might work in practice?
So when you create a transaction with Bobcoin, you use the aggregate information that is published by block producers, the stake pool operators in this case, to pick an exchange rate that is sufficient for a large portion of the block producers to process your transaction. The larger the percent of SPOs, of block producers, that your offer attracts, the faster your transaction will get processed. We call this percentage the coverage of your offer. If you pay too little or your coin is not widely accepted, it may take a while until your transaction gets processed. By using a popular coin at a reasonable exchange rate, you can expedite the whole process.
Okay, so in summary, bubble fees create a spot market for non-ADA fees.
So if you want to pay with your own coin, maybe a custom coin that you already own, so for example, in this multiplayer game I used as an example before, I've got this in-game currency, then I'm still faced with a problem. I mean, it's convenient. It allows access for me to the network despite not owning any ADA, but it's inconvenient because I cannot rely on the exchange rate between this custom token and ADA to be stable. Maybe tomorrow I'm going to pay a lot more than I pay today for the same transaction. So is there a way to reduce that problem, Aglos?
So to do that, we need one more idea on top of bubble fees. The issue here is that we would like to denominate the value of a transaction in a way that is predictable for the users. So one very appealing way to do that is to, instead of using the ADA coin as the target for the swap, we could use a stable coin which is managed by ADA. Now, this stable coin can be pegged to a basket of commodities or fiat currencies or a combination thereof that the users of the platform have voted in and they would like to support. And in such a system, you would still have ADA as the main mechanism for managing the stablecoin, but the target of the spot swaps for bubble fees would be the stablecoin. Now, before we dive into this though, let's return back and take a deeper dive on how bubble fees can be implemented in Cardano. How is it possible to replace the Bob coins that Alice selects in a transaction with the correct ADA fee? Aren't transactions supposed to be cryptographically immutable and thus impossible to modify? Manuel?
That's absolutely right. I mean, it is crucial for the security of the system that transactions can't be just written by anybody or even the block producers, that we can't have that. But there's another way to do it. So our idea was to add a second transaction. So we have the actual transaction which uses Bobcoin to pay their fees. So that's the Babel fee. And then the block producer who wants to accept those Bobcoins, they add a second transaction. We call it the fee-paying transaction. And in that fee-paying transaction, they include the fee in ADA to pay for the fee-paying transaction and the actual transaction with the main payload, the Babel fee transaction. So the only question is, how does the system know that these two transactions belong together? They need to be coupled in some way. Michael?
Sure. So this is in many ways, the key innovation that we came up with. And this is the notion of adding liabilities to the ledger accounting. And so I think the easiest way to show this is with this diagram that we have here. So this illustrates an example, just like we were talking about, where Alice wants to pay Bob 9 X tokens, which could be Bob coins. And as you can see, there are two transactions in this diagram with this little dollar bill on them. In the first transaction, Alice sends 9 Bob coins to Bob, but she also creates a second output, and that output contains 0.48 Bob coins and 16 ADA, which is the fee, but not actually, sorry, 0.16 ADA. 16 ADA would be a lot, but not in the normal way, but actually as a liability. So in fact, it contains minus 0.16 ADA. And this is a bit weird because normally we think of outputs as containing actual assets and, the value should all be positive. But the simple extension that we made is to just say, well, let's let them be negative. And then everything still has to balance. So what that means is that although Alice's initial transaction had no inputs containing ADA, the fee and the output containing the negative amount of ADA actually balance by themselves. Then we get the second transaction. This could be provided by the block producer, Stacy in this case, where Stacy provides some ADA, consumes the output that Alice created, and takes the rest as change. And if you do your sums and you balance this out, you realize that what happens is that Stacy provides the ADA for the first transaction, because in order to make the second transaction balance, Stacy needs to provide an additional 0.16 ADA, which is exactly what the first transaction needed. So it all balances, everything adds up, and at the end, Stacy comes away with the 0.48 Bob coins and slightly less ADA, and Alice never had to hold any ADA at all. And there's an implied exchange rate here, of course, which is based on the offer that Alice makes to Stacy or anyone else who was willing to complete this by creating an output that has 0.16 ADA and 0.48 Bob coins, and that says, well, I'm willing to make this trade at a 3-to-1 ratio, and if anyone thinks that's a good deal, they simply provide the second transaction, and that makes the resulting system balanced.
I see. So the point there that Michael, you just described very nicely is that there is like a transaction that introduces a liability and another one that matches it. But how will the system know that two transactions were meant to be connected in this way? Paulina, would you like to cover that?
Sure. So first of all, the second transaction, which is the one paying for the fees, consumes and hence resolves the liability output or the debt of the Babel fee transaction. So it pays the debt in ADA. And then secondly, the same output that contains the ADA debt also contains my coin used to pay the Babel fee. This enables the fee-paying transaction of the block producer to pay my coin into their wallet as for payment for services rendered. So the author of the second transaction gets the Babel fee of the transaction because they paid its fees to allow it to get processed. The author gets to choose, when constructing the output of the second transaction, what address the liability Babel fees go to. The second transaction can't be included without the first one because it spends the output produced by the first one, and the first one can't be included without the second one because since the second one resolves its debt. Finally, the two transactions go into the chain together in a transaction batch, as opposed to by themselves. Note that there isn't necessarily a unique transaction that is able to resolve a liability. It can be done by any transaction that provides the funds required to cover the debt and also spends the liability. Note also that in some cases, it's desirable to have a batch where it's more difficult to swap out one transaction resolving liability for another. This is the default case in some other systems offering atomic swaps, such as Algorand, where signatures from both parties are required on the transactions in order to perform an atomic swap. We can simulate this functionality within the liability mechanism with, for example, custom tokens with appropriate spending policies contained in some UTXO addresses that are spent throughout the batch.
Thank you, Paulina, for explaining this. Let's think about security now. Someone that produces such a transaction with a liability also has some coins that offers as part of the transaction. So how do we make sure that no one can steal the coins that are on offer as the transaction is submitted by the user in the open network? Michael, would you like to discuss that?
So while we are extending the accounting here, we have taken care to make sure that this is safe and won't result in anything unexpected happening. And so we have these two extensions to the ledger. We have the idea of liabilities in outputs, and we have this idea of transaction batches. But the key thing that makes this safe is that we restrict liabilities to only appear inside transaction batches. That is to say, once Alice, Bob, and Stacy finish this batch between them, well, Alice and Stacy finish this batch between them, the final UTXO set cannot contain any liabilities. So that means they're, as it were, they're only virtual. They appear for a brief period of time to handle this accounting difficulty between Alice and Stacy, but in the UTXO set that the ledger actually maintains from block to block, they never appear. And this makes it much safer. We don't have to worry about what would happen if someone created much higher volumes of some currency than were expected by this mechanism and backed them by an unsupported liability, because that simply can't happen.
As another safety measure to ensure safe operation of our mechanism, minting policies are always checked whenever the total supply of a token in the intermediate UTXO is either increased or decreased. So you produce some negative quantity and positive quantity, and the positive quantity increases the positive supply. So the author of a token's minting policy has the power to opt in or out of allowing their token to appear in a liability output by specifying this in the minting policy. It's important to be mindful of which tokens can be allowed to exist in liability outputs. Contract debt tokens, for example, should never appear in such outputs, as this could result in some adversarial behavior. But this is regulated in the minting policy validator.
Thanks, Pauline. I think that's very clear. Now let's turn our attention to the block producers, the stake pool operators that are one of the class of parties that are natural for covering these liabilities, covering the liability transactions. So there must be some way that can help users to do the price discovery and find how do they engage with a Babel fee mechanism. So how does that work? Nico?
Each block producer maintains a public table of all custom tokens that they are willing to accept as a fee payment. This together with exchange rates that they expect. This table of accepted custom tokens with their corresponding exchange rates from all stake pool operators is available to all users. This public information will guide the user to create an attractive offer.
So what if almost everybody access Bobcoin? Let's just make an example to see how this works. But some block producers, let's say, want 100 Bobcoins for 1 ADA, while others are okay with 80 Bobcoins for 1 ADA. How would that work in this case, Nico?
Okay, then in this case, the transaction issuer has got a choice. Let's assume that 10% of the block producers are happy with 80 Bobcoins, but 80% want 100 Bobcoins. You can pay the fee at a rate of 1 for 80, and then you probably will have to wait somewhat longer until a block producer accepts and pays for your transaction in exchange for Bobcoins. In this case, the coverage of your offer is quite low. Otherwise, if you are in a rush, put down a fee at the rate of 1 for 100 and almost everybody will take that offer.
Okay, that's clear. I think we understand now how the bubble fee mechanism works. But I'm still curious. Earlier on we talked about manners to protect users against fluctuations in exchange rate, which are usually inherent in this type of mechanisms. And we mentioned a stablecoin that could maybe help. Aglos, could you explain that in some more detail, please?
So the stablecoin can be managed by a smart contract on-chain. We can call this the decentralized reserve contract. And that contract will issue a stablecoin that now will also be capable of being involved in any transactions in the transaction layer of Cardano. Now, the stablecoin can be pegged to a basket of commodities and/or currencies. Now, this is up to the decision and the governance of the platform itself. Now, let's call it the stablecoin, basket equivalent coin, or BEC. Now, fees now can be targeted and denominated in BECs. So the stablecoin is used as the target of the spot swaps. Now, the key advantage of this is that the fees will remain stable with respect to the value of items that are in the basket. Now, the reserve contract will have to make adjustments in the way that it prices those BECs. So it should rely on an oracle that is feeding off-chain information about the commodity prices and monitoring their value in this fashion. By doing that, it is capable of adjusting the rate accordingly so that the value of the stablecoin will remain in par with the basket, no matter how ADA fluctuates. Now, this off-chain information can be provided by stake pool operators themselves, who will be rewarded for that service, just like for producing blocks. As SPOs are already incentivized to keep the system stable and to maintain their reputation, they are a natural choice as an off-chain data source. However, there might be other entities that are interested in providing this service. Another thing that's worth mentioning about this is that there could be multiple stablecoins that can actually coexist in the system, pegged to different baskets of commodities. Now, this further expands the concept of bubble fees, enabling different communities to accept their own currencies for transaction processing. And it aligns very well with the general vision of Cardano of being a global and all-inclusive financial and social operating system. This brings us to the end of this discussion. I hope you found it interesting. If you want to learn more about the concept of bubble fees and stable fees, you're welcome to read the technical reports and papers that we've written about the topic, as well as see the blog posts that contain further information, as well as videos that explain these concepts. Thank you for joining in this panel, and thanks to Manuel, Paulina, Michael, and Nikos for going over the concept of bubble fees and stable fees.